Hi, Matthew here on Wyzant, and today we're going to talk about the Pythagorean theorem in more than two dimensions. So this is the normal Pythagorean theorem as is usually learned in grade school, where you have a triangle with a width of A, a height of B, and a hypotenuse of C, and we find that A squared plus B squared equals C squared. Now, if we extend this into another dimension, we have a width of A, a height of B, and a depth of C, and we have D here, which is this long hypotenuse. We find that we can figure out this hypotenuse, the closer one, is square root of A squared plus B squared using the Pythagorean theorem. This up here is also C. And we square this, we add them together, we get A squared plus B squared plus C squared equals D squared. And so in 3D we get A squared plus B squared plus C squared equals D squared. In 4D we would get this except with E. And basically we just, as we add dimensions, we can just add the squared value on. Next to the actual problem, which is given, well, the first problem, which is given the right triangle A at 0, 0, 0, B at x, 0, 0, C at 0, y, 0, and D at 0, 0, z, what is the area of triangle BCD? And so if we draw a little bit of a diagram here, we have A is at the origin, B is along the x-axis, C is along the y-axis, and D is along the z-axis. And we have a shape like this. This is a tetrahedron. And so the question is, how do we find the area of BCD, of this face of the tetrahedron? Using, and there's a couple ways of doing this. I will do the proof for or kind of the conventional way, the first way you would think of, and then I will explain similar figures a little bit and why we can quickly solve the last problem where we're dealing with volumes in 4 dimensions. So as we know, the length from A to B is x, and the length from A to D is z. We know that this hypotenuse here from B to D must be square root of x squared plus z squared. We know that A to B is x, A to C is y, and so this hypotenuse must be x squared plus y squared. And finally, the C to D hypotenuse must be square root of y squared plus z squared. And so we're able to find each of these hypotenuses. We only know the 3 side lengths, and so we are going to use a standard but unusual formula for finding the area of a triangle, which is Huron's formula, which says that the area is the square root of S, which is the semi-perimeter, times S minus A, times S minus B, times S minus C. The semi-perimeter is half the perimeter, which is A plus B plus C over 2. We fill this in. We see that S minus A, I did it here, gives us negative A, and these all kind of look the same. And if we multiply the top all together, we get 2a squared b squared plus a squared c squared plus b squared c squared minus a to the fourth plus b to the fourth plus c to the fourth, all divided by 2 to the fourth, because there's 2 fours along the, or there's 4 2's along the bottom. If we expand out the right side of the top here, an a squared plus, or a squared times b squared, we fill in our values from here. We'll find that's x plus y x squared plus y squared times s squared plus z squared. And we see that we get an x to the fourth because it shares an x, because both this and this share the x side. And then we have plus x squared y squared plus x squared z squared plus y squared z squared. And so we get these three possibilities, these three combinations of squared squareds, or of squared times squared. And so in AC and BC, we'll get y to the fourth and z to the fourth, and we'll get all these same ones. So we get a total of this, the addition of these three gives us this, and this plus 3 times this tail here. On the right side of the top, a to the fourth is going to be x squared plus y squared all squared, which we get x to the fourth plus 2x squared y squared plus y to the fourth. And so for B and C, we're going to get a different combination of x squared z squared and y squared z squared. And we're going to have 2 to the fourths in each, which is going to give us 2 times x to the fourth plus y to the fourth plus z to the fourth plus 2 times this. We subtract 2 times this from, or we subtract this, the right side, from 2 times the left side, and we get this formula because the 2's cancel and gives us 4 at the end. You can check the algebra on your own time. And then we're able to split these up, and we get x times y divided by 2 squared plus x times z divided by 2 squared, y times z divided by 2 squared. And this is the solution to problem 1. But we'll notice that the area of one of the side triangles, aka if we look at this triangle here, ABC, is x times y divided by 2, because it's normally a square. You have it to get the triangle, so it's x times y divided by 2. And we notice that this shows up in our formula here, and this is because triangles, or the triangles make up similar are similar figures to each other, and so we can extend into 4 dimensions by, instead of looking at, or since we're looking for the volume of the tetrahedron, so instead of looking at the area, we're looking for volume, so the 3-dimensional space. We can extend to 4 dimensions, and if we look at the volume of, let's say, the A, B, C, D side, which actually I should write out quickly what each of these are. Or C, D, X, Y, Z, W. So we have these points, and so if we look at the ABCD volume, the volume made by these 4 points connected to each other, we'll find that the volume is divided by 6 to the squared. We'll find that the volume for ABCD is this. And so we have the x, y, and z. We have divided by 6 because it's volume. And we can do these for all four combinations. And as we know from adding dimensions, we just add the squared value. And so we can find that the volume for the tetrahedron BCDE, so everything except A, is going to just be, or the squared volume is just going to be the sum of these volumes squared, because it is a similar shape. So let me write the formula quickly. X, Y, W, X, C, W, and Y, Z, W. And so we get that the volume squared is going to be the sum of these volumes squared, or each individually squared. And this will extend into higher dimensions, and so you can find it's not volume, but will be I don't know, some sort of hypervolume in some sort of four-dimensional volume in 6D space. Will have the same relationship with the volume, or with the 4D volumes of its sort of composite parts, because of similarity.